Good morning, everyone. My name is Josh Salomon from Red Hat, and I'm going to talk about how we can optimize performance of small Ceph clusters. So the first question is, what's so special about small Ceph clusters? And Ceph is is built to scale out. It's built to work on large clusters, and the default values and the way it works for small clusters is not optimal, but we can improve it. There is another question: what is a small cluster? So actually, what's important is the number of OSDs. I'll show. I worked on a 3-node cluster. All those who think that 3-node cluster is too small, everything would be correct for larger clusters. In terms of nodes, the important part is the OSDs. The balancing of the PGs is partially statistical. It works better on larger numbers, and as I said, the default for small clusters, small numbers. That's one of the things we'll talk about. There are some kind of newer use cases for smaller clusters, for clouds, for small Kubernetes clusters, and there is no need to compromise the performance. We may not get the best performance with out-of-the-box defaults, but we can get good performance. And one of the things, it's easier to optimize smaller clusters because it's easier to monitor, and we can use it. There are some things here which would be non-practical to do on larger clusters. And in small clusters, each node is more important. For example, if we have 3-node clusters with replica 3, every node impacts every write. So if we have something in the node, some node burps, it impacts immediately the entire cluster, the writes, even if the system is not loaded. So we need to make sure that everything is working fine. All the tests that I did, everything here is based on the Mimic version. I will talk a bit about Nautilus. If you forget this, I have the Mimic here on my shirt so I can remember which version I worked. I worked on bare metal, virtualized, and containerized environment. I'll talk a bit about differences, but basically it behaves quite the same. So this is the deployment that I worked on. And excuse me if I'm not looking all the time to you. It's just I have the light right in my eyes. It's very difficult, sorry. So 3 nodes, 4 ATDs per node, 40 gig NICs inside the cluster, 1 RGW on purpose. We'll see later how to optimize RGW as well, and CostBench as a test driver. Again, all type of environments. And the first question is when we look at such a cluster is where do we expect to see bottlenecks? When we try to optimize this cluster, where do we expect to see bottleneck? So the answer is everywhere. Optionally, we need to optimize. It's a very complex environment. We need to make sure that the bottlenecks are moving all the times, but every single place you could have a bottleneck. So what is the importance of data balancing? So distributed systems are vulnerable to weakest link in the chain phenomena under some circumstances. I'm going to give an example about storage, but it's a Q-theory mathematical issue. It's correct for all type of other resources. And I'm not sure it's exact tight mathematical boundaries, but under these circumstances, we are going to have it. We have resources in shortage. For example, devices. We have enough clients, which means we have enough threads which use the resources. In this case, we are sending IOs. And they work like this. They send IO, they wait for the response, they send another IO, they wait for the response, send another IO. Under these circumstances, if we load the system more than its performance, we are going to have the weakest link in the chain event, meaning if we have X devices with, I'm going to speak HDD terminology, if you're going X devices with 100 IOPS and one device with 50 IOPS, eventually all the system will behave as if the devices are 50 IOPS, all of them. And this is, it has nothing to do with devices, it's more with the queue theory, how eventually the queue of the slow device will be full and other devices will look and wait for IOs. So, just for an example, if we have 99 devices with 100 IOPS, one device with 50 IOPS, what are we going to get total from the system? Like 100 devices with 50 IOPS. We're going to get 5,000 IOPS. If we have 99 devices with 100 IOPS and one with 200 IOPS, we're going to get our 10,000. The device with 200 IOPS just will sit half idle, and that's all. And the same is correct if we are going, we have not the speed, but the amount of requests going to the device. So if we have 900 devices with 400 gigabytes of data and one with 800 gigabytes, and we assume that the amount of requests is proportional to the amount of data, then eventually the device with 800 gigabytes will get twice the amount of the request. It will become as if it's slow, and the entire system will go to half the performance. On the other hand, if we have 99 devices with 800 gigabytes and one with 400 gigabytes, the one with 400 gigabytes will get less requests, performs normally at half its speed. So the numbers that we are going to get is, if we have one device which is not balanced on the wrong side, we're going to get half the performance. If we have some devices, small amount of devices which perform better, we won't see anything, but that's not that critical. So I'm going to talk a lot about this, how we make sure of this. So how Ceph is balancing the capacity over the system. And this is important. By the way, when I said before about the weakest link in the chain, we talk about sending requests randomly to the devices. We get this automatically from Ceph. We ask for an object or a file or whatever, and it's randomly spread across our devices. We don't know how it works. So we're already there. So the way that Ceph balances the capacity is through the placement groups. So first of all, the capacity is divided to groups of power of, on the size of power of 2, 128, 256 or so. We have power of 2 chunks. Then we have the number of PGs that we allocated to this pool. And then these chunks are distributed among the PGs. So if we have 128 PGs and 128 groups, we have 128 PGs, we will have 128 chunks, and we'll have one per each PG. But if we give 100 PGs, then we will get still 128 chunks, because it's always power at 2, and we will need to split to allocate 128 chunks into 100 PGs. So we will have 28 PGs with double the capacity, and 72 others will have half the capacity. So we get the capacity is not spread evenly among the PGs. So this is one of the rule of thumb. That's the explanation why we always want number of PGs to be powers of 2. If we have too many and we think there are resource memory concerns and we want something else, maybe put between 2 powers of 2 in the middle, but don't do something in which you have 10% of the PGs have more capacity than the other 90%. In small clusters, you may get imbalance over the devices because of some placement. It's important. Okay. So we have several balancing rules. I'm going to take about 3. So the one, we want same number of PGs per OSDs because eventually the way the I/O path goes, we get a request, it's mapped to a PG, from the PG to a device. So if we have the same number of PGs per OSDs, it means that we will have the same number of requests per device, which is what we want, because if we already saw that if we have one device with more requests, we get a slower performance. Then we have balancing rule number 2, which is actually usually takes precedence, but it's here because it's not related to performance. We want that devices should have the same utilization. We want all the devices to be 50% full or 60% full or 30% full, because when we have device which is 100% full, we start getting errors. We don't want to have all our devices of 800 giga, one device on 600 giga, and then when the system is only 75%, we start getting I/O errors because the 600 device can't perform writes. So we want to split everything evenly. Otherwise, we have a lot of operational issues. And this rule usually takes precedence because it's more important the system works and it works very fast. And when the devices are not on the same size, we get a nice effect that these rules are contradicting. So that's if we need to think about what we do if we take systems such as Ceph and put devices with different sizes. It has performance impacts. The third rule that we want to have is that we want the same number of primary PGs per OSD. Primary PGs, when we use replicas, is the PGs that perform the read operations. So if we have replica 3, we get each PGs mapped to 3 devices. So write go to the 3 devices, but reads goes always to the primary PG. So we want the primary PGs to be split evenly across the devices, because on heavy read loads, we want the load to split among the devices evenly. The unfortunate thing here is that this rule is not implemented yet in Ceph. So we need, and I'll talk later, what we are going to do and how we're going to monitor and try to improve this issue when the primary PGs are not balanced. And we don't have good tool to monitor it. We have some techniques that can improve the situation. So what are the conclusions from this? The number of the PGs should be power of 2 or middle between power of 2. Small number of larger devices in the pool is bad for the global pool performance. Small number of smaller devices relative to the average size. It's a local effect. They will not work in full performance, but it doesn't have a global effect. And if we have heavy read loads, we need to check and see how the primary PGs are balanced. All of this is correct for replicas. For ECC, in any case, it's not for high performance for various other reasons. But the behavior is different with ECC than with replica. So what balancing tools we have in Ceph? We have several tools. Some of them are new to Nautilus. Some of them are older, and I'm going to take. So we have Balancer, which actually does quite a good job, but it's not available on all the older versions. We have the older mechanism of OSD crush reweight, which is something more manual. Again, it can work on smaller cluster completely challenging to work on larger clusters. We have a new tool of PG Autoscaler. Sage talked about this in the keynote. And we could change the number of PGs and even reduce it also. Sage talked about this in the keynotes. So what is the balancer? The balancer is a plugin that can optimize the placement of PGs across the OSDs. It's, as a module plugin, it needs to be optimized. And then, like we see more example of this, in order of this to enable it, you need to give 2 commands, not only 1 command. We'll see other places. You put it on and set the mode. If you put it on, it gets an empty mode and doesn't do anything. So it's not enough to do Ceph Balancer on. We have 2 modes, crash compatible. It's for all kind of clients, for all the new clients. But it works good, but not great. It has some kind of edge cases where it doesn't do a perfect job. We have a UP map mode, which requires newer clients, but it should achieve a perfect mapping, which means that if you look at the OSDs per pool, all the OSDs get the difference between the higher number and smaller number is 1. It's not exactly plus minus 1, it's 1 difference. So all the OSDs get the same number of PGs mapped to it. So that's what the balancer does, it's mapping the PGs and starts to move data. Typically, from what I saw, it moves small amount of data, 3 to 5% of the data is moved. Depending on the system, it takes some time. It's not critical, but it also has some limitation to the improvement it can do. And this is what it is done automatically. In addition, you could trigger it manually to get better balancing. So you can evaluate the current PG distribution. You could evaluate the distribution for a specific pool. Well, we all know that not all the pools are born equal. Usually we have a small amount of pools which are way more important, so we could do this per pool, especially when it involves moving data. We don't want to move data for a pool of very cold information. It's not really important. We can create a plan. So we could create we ask the balancer to create a plan for a pool. We can evaluate the plan, see whether we think it's worth our effort to do this. Again, we talk about data movement, it's expensive, and then we can execute this. So the balancer can work either on the background all the time, or specifically on a pool or manually. The thing is, again, it improves usually, or it improves the situation, but the improvement could be marginal in many cases. Why is it? It has limitations in the way that it works and moves the data. And we'll see later what can give a much better performance. We have the crash reweight. Again, from the test that I did, I recommend using this if you cannot use the balancer. It's an older mechanism. You could change the weights for a single OSD, or you could do some reweight by utilization, which changes the entire weights for the crash map according to the utilization of the devices. It's challenging because the results are not directly predictable, and if you need to do more than one step, probably data would be moved several times. It would be more expensive, more complex, and not so easy to balance larger clusters. If you have very small number of OSDs, it's worth. But if you have an older version or you use older clients and you cannot use the balancer, that's your only option. So we could have we could reweight a single OSD, and could, if the weight is larger, then more capacity would be moved to the OSD. If it's smaller, it would be reduced. Or we could do reweight by utilization and let some kind of algorithm decides on the new weights for the entire OSD map. Then we have a new tool that Sage also talked about this in the keynotes. Setting the number of PGs per pool was some kind of black magic. Now, it works quite fine on larger systems. On the smaller system, the defaults are too small, and we'll talk about this, because when you have smaller number of PGs, the statistical fact of the crash of the placement of the crash algorithm creates a situation, and you have more fluctuations and less chances of getting relatively balanced system because small numbers. The big numbers give a lot of advantage when you do it statistically. So we have the Autoscaler that can give you the recommended number of pool of PGs. We also have new feature in Nautilus. We can decrease the number of PGs. I tried to decrease once number of PGs using some kind of mechanism, create a new pool, copy all the data, delete the old pool, rename the new pool to the old. I ended up with system not functioning. So reducing the number of PGs is a very, very nice feature. Regarding the auto balancer, it has two modes. One mode that it works automatically. You get more data than the number. It changes number of PGs. Changing number of PGs has huge impact on data movement. Like doubling the number of PGs could move about 35% of your data. It's a long. There is another mode which just warns you. So my use case, you are writing e-commerce application, and everything works fine, and then Black Friday comes, and you have a lot of traffic, and the system decides that you need more PGs, and the data starts moving in the background. If you are sensitive to your performance, use the warning mode. When you issue Ceph -S, you would get warning that number of PGs is not okay, and then you can decide to change it when you want it and not automatically. So we have the commands, and again, be careful. If you need max performance, be careful to use the automatic mode. It will have impact on performance. On the other hand, you could help the autoscaler. And you could help the autoscaler by telling it ahead of time what are your expectancy of data per pool, and if it would do the autoscaling based on this. So you could say either in capacity or in percents what you expect this pool to be out of the system. So you could say that the second line, that the target size is going to be 100 terabyte, or you could say it's going to be 90%. 0.9 means 90% of the system capacity. So it will take it into effect at the mid. The first line target PG per OSD, the amount of PGs per OSD, probably for a small system with small number of PGs is too small. You may want to. Yes. Sorry, just I can't hear you, just literally.
Sorry, should you set that ratio when you build a new cluster if you know you will eventually fill it?
Yes, yes. The thing about this is, if you use, especially if you use the automatic PG number, yes, you want the expected number to be set at the beginning, because when you change a number, you need to move a lot of data. Yes. So we can have the number of PGs per OSD changed for small number of OSDs. It's important. The default is good for large cluster. It's less optimal for smaller clusters. We could set the expected size. You could say the minimal number of PGs per pool, and you could set the number of pool creation times. All these are techniques that may help you prevent the autoscaler to do things incrementally. Like you start a system, it's empty, you have small number of PGs, then you start putting data, then you need more PGs, and it's doubles it. You put more data, it doubles it again, and then you do an iterational process. And eventually you end up moving a lot of data many times. So if you know the numbers at the beginning, you'll get the target number at the beginning, and then you won't move data. Yes. And actually, if you use this tool well, so you need to extend the PGs per OSD at the beginning, and then you set the right numbers, and you do it like a calculation, you're probably in good situation. But don't leave it to make decision without hints as you work, if you're sensitive to the performance. If you're not sensitive to performance, it's a different thing. It's rather conservative, so it takes the decision to change the number quite late, when it's sure that, so it's the ratio between the number of PGs and what it thinks it should be is larger than 3. And it's a new feature. If you want to look at it, there are a lot of more information you could look at it. If you use it smartly, it's a nice feature. Excuse me. Changing the number of PGs. OK, if you are not using Nautilus, and you don't have the autoscaler, then your best chance of getting better balancing is a larger number of PGs. As the number of PGs are larger, you have better statistical the distribution, and then you'll get a better balance system. Especially, we'll see when you look at a primary PG distribution, which is only statistical. You can't influence it in any way. So again, that's if you don't have any other way, and you see the system is not balanced, and larger number of PGs. That's what you can do. More PGs, you can reduce in Nautilus, but in Nautilus we have other tools. We talked about it. PG number should be a power 2, or in the middle, as we talked about it. As before, you need to issue 2 commands, not 1. pgnum and pgpnum should have the same number. If you enlarge only pgnum and not pgpnum, then the algorithm cannot move enough data, so it won't improve the balancing. That's basically everything here in this slide. And then, so this was all kinds of tools that we have. And now, how do we check the cluster balance? So actually, we have the data distribution we could get from Ceph OSDDF. We get two numbers at the bottom, the std-dev and min to max. std-dev is very good indication whether the system is balanced or not. A 3.5 is very bad. Obviously, we want to be near 0. Ceph minus S gives us something very important. It tells us whether the system is healthy or not. We don't want to do all kinds of balancing operations when the system is not healthy. Things are moving. We are not sure what's going on. So it's better to check the system is OK before we do this, or before we even test that the system is balanced. Because if we have rebuild, we may get something which is not well balanced. Maybe we need to balance it later. But if we are doing it now, it may not be good enough if the node is failing or multiple devices. So we want to issue Ceph minus S to see everything is OK. And then we could see the data distribution among the devices using Ceph OSDDF. And we don't have existing tool to show the primary balancing, primary PGS balancing. And this is what one of the things that you could take from here. We have a script to do the primary PGS balancing, which can be found in GitHub. First of all, it's doing the Ceph minus S and Ceph OSDDF, so we see the information about the system. And then it actually iterates over a lot of information about the OSD and prints the number of primary PGs per OSDs for this pool, and then the total PGs and distribution, the primary plus the replicas, and bottom line statistics, one number that could give us enough information that we can evaluate what's going on. So if we see here, so this is again from my pool with 12 OSDs. We say with 128 PGs, we get this std-dev. Then we have the bottom is output from the script. The important number is marked, max to average ratio for primary PGs. Max to average ratio because if we get, again, random requests, we're going to get one device, in this case, going to almost twice the request as the other request. And what it actually means, as we said, weakest link in the chain, we are going to have a bit more than half of performance of the cluster, in this case, on read operations. So we see also min, max. What's really important, max to average is a very good number. So std-dev and max to average are good indications how the system is balanced. And now for the impact of changing the number of PGs. So we just need to remember each one of the operation here, which is I'm going to double the number of PGs to show information, moves about 35% of the data, even of my very small 12 OSD system HDDs. It took hours. Actually, I was doing this overnight. So I was finishing my day, issue the commands, and come in the morning to see that it's OK. It takes several hours. So be careful of this. It's not something we want to do many times. So we have 128, then we go to 256, and we see the std-dev is approximately half, and max to average also half. I say half because the optimal number is 1. So we went from 1 to 8 to 1 to 4. std-dev optimal number is 0. So we went from 1.8 to 1.4. So it's approximately half. Then we do another doubling, and this is a real-life number that I got. I didn't do anything specific. So again, half the std-dev, and again from 1.45 to 1.24. And then that's all. For this, it improves better, and I may show it improves better if you go larger, but you can't make, there is a price of more PGs. The price is in memory, and we'll see it later. You don't want to put there 4096 for 12 OSDs, it's too much. So you need to be careful. And eventually, I have some test results that show the impact of the balancing on the performance. So this relates to the numbers that I've shown you before. The graph starts at 750, not at 0, so it's not huge improvement as it seemed, but it's a substantial improvement. And we could see that from 128 to 256, we got huge improvement. Then for 512, we got additional improvement, and then a reduction when we go to 1024. Over the next slide, I'll talk a bit about this. But I can tell you that from previous experiences, I knew that the number that I want to get is around 1,300 megabytes per second from this system. Between 1,300 and 1,400, that's what I got from bare metal, and this was a containerized environment. And something bad happened here. And this brings me to the first slide when I said, where can we have bottlenecks? This is a situation where the bottleneck is not the devices anymore. They're stopped being devices. So there is another thing that you should do when you want to do this. And this is, so we reach another bottleneck, and it's going to be solved here. And next aspect was the RGW. As I said, I had single RGW, and it was on purpose. And we can add memory quota to the container and CPU, but this wasn't a bottleneck. But the bottleneck was regarding the objector attributes against two attributes that had better go together. These are numbers, they should be enlarged and reduced together. It's like the depth of the queue all over the system of asynchronous operations. Actually, what happened is that we got to another block by the queue of the asynchronous operations, and the minute we enlarge this number, and I played with various numbers, we see the performance improvement. Still, the 1 kpgs is a bit slower than the half kpgs, and I can explain why. I couldn't find exactly what happens for very prosaic reason. The lab that I was using was literally closed. Shut down, and the machines were moved, and I couldn't continue my test here. But we see here, this start with 0. The graph starts with 0, and we see about 31 improvement. We got to 1250 megabyte per second, 1250, which is reasonable where I expected to be. So it's a quite optimized system from what it. But we had another issue. Enlarging the objector size required a lot more memory from RGW. Now I worked in containerized environment when I gave RGW the memory quota. What happens when containerized environment, when you get to the memory quota? You start swapping. When you start swapping, well, that's a different story. The system. So even though the peak memory, I gave 8 gigabyte memory, even though the peak memory that I saw when I enlarged it, the peak memory was about 8.2 maybe, 8.1. When I got to 8, the system stopped performing because of the swapping. So beware this, and the objector parameter has a global impact on other components. It's not only in RGW. RGW here was the memory hog in this specific situation. So beware of swapping. Make sure when you do all these kind of changes, you need to monitor other things. If RGW works fine without enlarging the objector size, when you look at it, watch it. It's as normal as any performance test. So, summary. 1 minute late. For small clusters, use relatively more PGs than for large clusters. The balancing over a small number of PGs per pool doesn't work well. Check your balancing. Look at it. Look at other bottlenecks. CPU network, I didn't talk about this, but CPU network go together. Today, if your NICs are not offloading the load, maybe that you get very fast connection, but you don't have any CPU left for other things. Beware of swapping. And consider re-architecting the cluster for QoS. I mean, I use one client and one RGW. If I want to have different QoS, I would put two different RGWs clusters, one with a large size of objector, which would give better performance, and another which can give less performance. That's okay, but takes less resources in order to do it. In some cases, it could be a reasonable thing. And if you use Nautilus, there are some really cool new tools that should help you do this all really easily and wouldn't give me the opportunity to talk here. So that's all. If you have questions, I will be now in the booth of Red Hat, and I'll be happy to talk with you. And that's all for today. Thank you.